Hey, it's me, Steve, and welcome to the second episode of Geo-Files. Today's going to be a loaded episode. There's three things I want to cover. I want to cover geologic equipment in the field. I want to cover the importance of note-taking, and I also want to cover how to take the most important measurement in the field, strike and dip with a Brunton compass. So it's going to be a little loaded of an episode. I also need to trim my beard soon. My mustache is starting to curl up. Maybe I should change my name to Jacques the Douche. But anyway, when you go out in the field to either, you don't need to be making geologic maps. Even if you want to describe an outcrop or whatever, it helps to have a backpack. Now this, I generally don't take this with me, but it's a good case. It's a Pelican case. What's in here? Not a gun. There are some things you should always have with you. I carry a GPS receiver. Alright, this thing is accurate to 5 decimal places. It does really good for a little, I mean, if you looked at some of my other videos, you've probably seen it in the field. It's just a little handheld receiver Magellan job, but it's never failed me, and I've had it for almost 10 years. You need a hand lens. The cord keeps it around your neck. This is my 10-X1 for looking at rocks in detail. It's basically a tiny magnifying glass. And Ezra's joined us. This is a hand pentrometer. I used to use this a lot in my geotechnical days, not so much anymore, but it measures in tons per square foot of resistance. So if you wanted to know, this is more for doing unconsolidated sediment work, like for surficial geology, but it is calibrated, and say I push on something and then it gives way, starts to push through right there. You measure from the ring. I have 1.5 tons per square foot in that case. That's not a very strong resistant unit. Digital camera. This isn't the one I actually use. This one died a long time ago. But the reason why I have a digital camera and I don't generally take pictures with my phone is because these have optical zooms on them, and your your phone doesn't. It's a digital zoom. So basically, zooming in, you're not increasing the pixels. You're just taking a picture of a smaller area, as if you were just to crop a tiny bit. Plus, the digital camera is a lot more resilient. I don't want to mess my phone up. Should always have a lighter. A couple batteries, AA's, which are for the GPS. I also have weak hydrochloric acid, which I mix myself, 3 to 5%. Here's this, and here's the dropper. That's for testing carbonate rocks. Limestones react very vigorously with hydrochloric acid, and dolostones to a lesser degree. There are flashlight, tape measure for directly measuring units if actual thickness is important, like accurate thickness. This one is actually in tenths and hundredths of feet, along with inches. Like I said, I still stuck on imperial, and the foot is a more useful measurement in the field. And why divide it into inches when you can just divide it into tenths and hundredths? So I use this tape measure. You need sample bags. These are just plastic Ziploc bags. And in a later episode, I'm going to go through how I number these and catalog these and then put them away for permanent storage. There is a method to my madness. A rock hammer. This is an 11-inch one. I had my one from field camp for like 10 years and I left it somewhere. So you want something like this where the handle goes all the way through. It's one solid piece of steel. That way it's not going to fly off. They do make special rock hammers, but I mean a Home Depot run for an East Wing will work just fine. I don't generally chisel much, but I have. You can tell by the back. I've done it before in the past. I use this at 99% of the time to break off rocks, get fresh surfaces. And our second most important piece of equipment in the field, the Brunton compass. I'm going to go into this in more detail in a little bit, but I just want to show you basically what it looks like. I don't think you can see the books. But that's basically what mine looks like. This is what we call a quadrant Brunton compass, and there's a reason why I prefer this to the standard 360 degrees. But we use this to take strike and dip, repair dips, plunges, things like that. But the most important piece of equipment in the field, and you have to know how to use it properly. Your field book. These are some scales I've made. You can put these down for scale on a rock so you can get exact measurements. You don't need to do that, but I do. Sometimes I'll use coins. There's two types of books I mainly use. This is them. I'm actually on book 14 now. But this one here, they're right in the rain. It's important to remember that these books are water resistant. They are not waterproof. In a downpour, they will get wet and fall apart. They are also, because a lot of consultants use these, I'm going to say this twice. These are made to be written on in pencil, not ink. Let me say that again. These are made to be written on with pencil, not ink. Ink smears, okay? This one, you can even see here, it's fading on this, and this is the part designed for ink. But the actual pages are made for pencil writing. And you ever try to write in the rain with a pen? Yeah, it works real well. Markers are even worse. But basically, the field book, I do fill out the page of contents. All right. Here's just some of the inside. Here's a diagram I drew. Trying to see if I have any blank pages in here. This is an outcrop right there. Yeah, I don't think there's any. This is also a plan view of an outcrop. Yeah. And any page you don't use, you should fill the book as much as you can. But I mean, if I generally, the way I do it is I'll go to a certain area, all right? And if I'm going to go along a transit, I use my GPS, and I'll have, this is actually continue, like here, I put my title up here, the date, who was with me, if anyone, if not just myself. I don't generally put light and weather data, although some people require it. These are my sample designations. These are samples I took and their numbers. But this is a continuation, like I said, from the previous book. But generally what I'll do, if I do something like this is also continuation from something else, but this is stop 3. I'll give the GPS, I'll do my pictures, I give a good picture description. So this way is why I use the digital camera, So I can take a picture and I know exactly the order and whatnot, and any picture that doesn't turn out, I delete. I log them as I go. Sometimes I give description units. I have strike and dip here. Down here I give a quick graphic representation, and then we have stop 4. And sometimes I'll divide them into 5A and 5B in case they're like within 100 feet of each other or something. But that's how I log them, and I'm as detailed as possible. Even if I take pictures of something, sometimes I'll draw it, because the picture, you may not get the full effect if you don't draw it and then go over it. So that's why I do that. Now, the second book, these are a lot more expensive. These, I think, are $3.50 a piece, come in packs of 3. I get all these from Ben Meadows. This one is hardbound. It's a lot thicker. I have 2 of these, Canada, that I've been working on when I do my Canadian work. And last time we were up there, it rained. And you can tell some of the pages are a little frayed and dirty. But once they dry, they're good. And here's a blank page. And what's good about these is because it says location project / client if you're doing it for work. There's your date. And down here you generally put who's with you, or you can put light and weather data. It's just a blank line for whatever someone might require or you might need. Okay, but here you have 2 sides. This side here, you generally take your notes. But if your notes continue, you just continue over the graph. The graph is good to have if you need to draw something, but it's not necessary. You can just continue your notes over, and you need to fill it as much as you can. Never rip pages out of here. If a page is totally foobarred, just exit out and sign it with the date of why it's garbage. Because you may think it's garbage, but someone else may need to pick this book up and figure out something that you did. Yeah, and I use both sides to draw diagrams. I just fill it as much as I can. Because like I said, I think these are like $20 a pop or something. So they are not cheap. But the good thing about these, unlike the other smaller field books, is that if you go into the back, you have abbreviations that you can use for the book. So if you write CHL, someone knows what that means. It also has awesome triangular diagrams. So, I mean, I look at a lot of these rocks, especially in Ontario. There's a lot of Archean rocks, but I never remember this. I need to look at it to figure out what to actually call it. So this comes up huge. This is a sandstone one. I don't like this one. There's another one I use, but it's good enough. I mean, it's detailed. You can use it. Some measurement conversions and grain size scale. It has U.S. standard sieve sizes here. I believe, yes, this is in Wentworth scale to describe grain sizes. Geologists, when we're doing geology, we use the Wentworth scale, and so does USDA. If you're doing geotechnical, they want to use USCS, and that's where this comes in. USCS is not a logical system. That's a rant for another time. The Wentworth scale is a very logical system. Plus, very fine sand is about the smallest particle you can see with the unaided eye. And even has this, so you can figure out your deviations of particle sizes. One for dark and light. Relative percentage of particles. Metamorphic rock classification. Basic mapping symbols on this side, which we're going to get into later. Do they have strike and dip on here? They actually don't. Alright. Well, I'm going to talk about that one anyway. Oh wait, maybe they do. Here's some more. Yeah, I forgot about this. Geologic map symbols. More of them. Here's your standard strike and dip symbol. Right here. Remember I said it was a squat looking T with the number that goes near the small part that's your direction of dip? This some more geologic map symbols. This is a classification for carbonate rocks. I am not very fond of this scale. It works really well if you've got a lot of fossil debris, but other than that, I'm not a big fan of it. It's over here, but you can use it. I have been known to use it from time to time. And this is a geologic time scale, the one that the GSA releases. This is version 4.0. This is the most recent version. I'm not going to go into any detail on this. I've gone into detail on these before in GeoRants. But that's why this book is pretty awesome. So, as of right now, I've covered some of the basic tools you'll need, okay, in describing geologic outcrops and doing mapping in the field. You can also take other notebooks with you. I do that from time to time. Stuff I know isn't going to get wet. If I need more space or I need to do quick calculations or something, I will use other notebooks. But that's the first part of this episode. Now we're going to talk about... actually, I did the importance of field notes, so I guess that part's done too. But now I'm going to show you how to use the Brunton compass to get strike and dip of a plane, okay? That is the most common measurement you will make with the Brunton compass in the field, and it's very important. Okay, it's time to go over the Brunton compass. Okay, now if you look at the face before I get into naming what these are, I'm going to talk about the face first, because here I have two different types of faces. The face on here is what we call the graduated circle. It's what has the degrees on it around the edge here. That's your graduated circle. There's two main types geologists use. The azimuth one, which starts at 0 and goes all the way to 360. I don't use that one, and I'm going to explain why. Then we have the one I use, which is divided into quadrants: north, west, east, and south, and it goes 90 degrees, 90 degrees, 90 degrees, 90 degrees. And there's a reason I prefer this as opposed to this. But first I'm going to talk about something. You look at this and you're like, huh, west is backwards. It's actually not. This thing, the Brunton, is designed to where you point it, wherever that north arrow is, the north part is pointing, that is the direction you're facing. So I am facing right now south 80 east. All right, that's a direct reading from the north arrow. Okay, because if you think about it, if you're looking like, let's see here, north is this way. North is this way, all right? And my compass is reading, I gotta get this away from a little bit. My compass is reading due north. Okay, so I'm looking north right now, straight. You can kind of see my face, looking north. So west should be this way. Should be off that way, where my finger's pointing. So I rotate myself, and my north arrow is pointing west, even though it's on the opposite side of the compass. That's because it's made to do that. You face south, it'll point south. Face east, it'll point east. It's designed that way. A normal compass isn't. It has east where it would be as if you were looking at a map. But that doesn't help you if you're trying to actually orient yourself. And these things aren't cheap, by the way. I have two. These things are like $450, but they're great and they last forever. This one I've had for almost 20 years and has gone in for service once to replace the mirror part, and the compass needle was starting to stick. The second one I've never even used the second one. It's brand new, unopened, and I've had it for about 5 years. But so the reason why I use this with the 90, 90, and 90 is because when we write measurements in the field book, you can, instead of saying like north 45 west as a strike, you could write, you know, what is it? 310 degrees. But see the problem I had there with that? this, you have to do math in your head if you're not used to using it, okay? And there's sometimes you'll put the compass down, say this is your reading, that's your north right here, but you can't see it. There's a rock ledge here or something like that. So you've got this. This is directly 180 from this. So this reading, and we always read strike from north, although your reading at this end of the needle will be south 45 east, you know 180 degrees from that is north 45 west. You don't need to do any math. You just read the opposite, and you can just figure it out that way. So that's why the quadrant one is a much better tool. Now I'm going to talk about the parts. Now, people call different parts different names. Where I pulled these from, here's the references. But what you can do with the Brunton compass, you can get planar and linear features, deformation. You can get attitude of dipping planes, which I'm going to show you. Plunging lines, I'm not going to show you in this episode. Measurements and attitude of dipping planes, and plunging. Measurements of attitude by using a map. You can actually use this in conjunction with a map. And I still use a manual map in the field, paper map in the field if I even take one with me. There are really high speed, like programmable things. I forget what they're even called, but they cost a fortune, and no, I don't have one, so I still do it the old school way. So those are some of the things you can do with the Brunton. But you look here, I'm just going to hold it up so you can see it. I'm not going to talk about this. This shows you how to do line of sight. You can look at that, zoom in on it if you want. It just shows an example, but I'm not even going to show you how to do that this episode. But basically, this is how it's oriented, all right? You have your bullseye level, which you're going to use, that's this yellow one, which you're going to use when you take your strike, okay? You have the magnetic needle, obviously self-explanatory. It's the same as it is on every compass, and when you turn it, it moves. This is your sight holder. This is your rear sight. This is your azimuth scale index, or your graduated circle. You have your mirror, which is used for other techniques. It's not used for strike and dip, but I'm not going to show you any of that here. This is your front sight. Okay. This little white thing right here, when you close it, it locks. You should not leave this out. I'm just showing you. It locks the needle where it was, so it doesn't drift and whatnot. It helps preserve the compass's long life. You have the inclinometer, this thing that I'm moving right now. That's the inclinometer, and that's key for getting dip and also shooting other things. But I'm going to show you, like I said, how to take strike and dip. But if you notice, it goes 90 degrees this way, 90 degrees that way on your inner circle. That's because if it's oriented, what you want to do if you're getting a dip is you move it to the green bubble is level. And then in this case, you read it off the long line. In this case, my dip would be 38 degrees. So that's why that is important. You need it to get dip. That's basically the important parts that I'm going to cover here. And now I'm going to show you. I'm going to first show you what strike and dip are, and then I'm going to actually show you how to get it with the compass. Okay. What is strike? Well, we do everything off north, and on most maps, that's up. So we work everything off north. Okay? Like I said before, strike is simply the connection of 2 points of equal elevation. Say you've got a planar surface, just in space. Say you have, you measure the elevation, let's say 5 points. We'll say units don't really matter here. We'll say this one's 490. We'll just say feet, meters. It doesn't matter. Oh man, I cannot write today. Okay, so these are your 5 points. All right, this is just some sort of plane that kind of goes down in elevation, comes back up. Actually, that's probably not a very good number. I should probably use more like 5. There. That would probably be more of a perfect plane. This is just guesswork. Distance isn't relevant for this example either. But there is a strike here. I can get the attitude of this. That's not a good number either. Okay, I can get the strike of this planar surface just off these numbers. Remember I said strike is the straight line distance between 2 points of equal elevation. Doesn't matter how far apart they are. They could be 5 miles apart, they can be 5 inches apart. It doesn't matter. You're using it to get the orientation. Well, you have 2 points that connect here. All right. Now, if that's north, we do have a protractor we can use to get the strike. But now when you write strike, it's always relative to north. Even though I might be facing this way, which would be southeast, I'm still going to give it as northwest because it's flat. It doesn't need to be. It's not like dip, okay, which has to be perpendicular strike. It's 2 points, it's just a line straight. Okay, that's all it is. So you could refer to it to the southeast, but nobody does that. So we'll just say that from my north, that looks to be about 40 degrees. We'll say from north, this is north, we'll say that angle is 40 degrees. Well, how would I write that? That would simply be written as north. Remember, it's always going to start with an N. Always going to start with north. N, always. Okay? And 40, you don't need the degrees. You just write the number. And it's going west. It's going 40 degrees. It's 40 degrees west from north. So north 40 west would be my strike. Okay? And this would be south 40 east, because remember it's an exact opposite. But we don't do it from south, we do it from north. So my strike here would be north 40 west in this case. All right? And we always say, like, you know, like I said, this is north 40 degrees to the west. If it was this way, 40 degrees this way, it would be north 40 to the east. It's always going to be north, a number, west, or north, a number, east. That's how you're always going to write strike. It's going to be one of these two. North, some number west, north, some number east. What if this is your strike? Due north-south. You just write it. You write your strike like this. North-south. Same thing if it ends up being due east-west. You just write east-west. And then your dip in this case has got to either be west or east. And in this case, your dip is either going to be north or south. Okay. So that's the concept behind strike. Now I'm going to talk about dip. All right, so I still have my north 40 west here. And if I was to graphically draw that on a map, that's my strike. That's about north 40 west, if that's north. Okay, so that's my strike. So I've already explained that. Now what's dip? Well, dip by definition is perpendicular downslope to strike. So if I have a north 40 west strike, my dip can only be southwest or northeast. I can't dip along strike, because if I dip along strike, I no longer am connected to 2 points of equal elevation. And what you're trying to get at that point is what we call a plunger bearing. But that's this talk for a different time. So if I have north 40 west, my strike is either going to be to the southwest. I mean my dip. My dip is either going to be to the southwest or the northeast. If I have a, just say north 40 east strike, which would be this way, my dip is either going to be to the northwest or to the southeast. All right. So, and we would draw that perpendicular. If, say, your dipping downslope is to the northeast, that's the symbol you use. It's perpendicular 90 degrees. And when you make the measurement with the Brunton and get your dip, so you have your strike, and say your dip, you get it with your clinometer, and you get 30 degrees, you just write it like that on the map. All right? You don't need to put north 40 west because your map's oriented to north to be able to figure it out. It can be measured directly from a map, and your dip is, they'll know it's northeast because of this, and it's 30 degrees. But if you're going to write that out, it would be north 40 west, 30 northeast. And just something else too. Say this is my strike and dip. Okay, that's my map symbol. That's what I'm gonna write on the map. And my north is still north. That's about 10 degrees from north. Or actually, that's probably, okay, let's say for the sake of argument, this is 5 degrees west from north. So my strike would be north. I could write 05 west. I generally don't. I'll just write north 5 west. And if my dip's shallow, I just change that to a 5. I'll write 5. Now this is where you got to be careful because this is a southwest dip. South. You got to make it look like an S. But if not, people will be able to figure it out. I mean, you're not going to have a west 55 west as somebody, so even if you write it sloppily like this, no one's going to think that's north 5 west S or 55 west. They're going to know that's to the southwest as long as you're consistent. Okay. Yeah, you could write it like this too. But that just seems to add extra space, take up extra space for no reason. So I generally just write it like that. So, how do we get this measurement in the field? Well, first, you find yourself a blackie. Yes. Hey, buddy. How are ya? How you doing, bud? Sorry, it's blackie break. Hey, buddy. All right. I gotta set something up here. I'll be back in 1 second. Blackie, say hi. What's up, buddy? Okay, what better way to show you how to get strike and dip than is to do it on an actual piece of rock. This is petrified wood from southern Indiana, cut and polished. I'm going to get strike and dip. This is very flat plains. How obviously reality in the field, rocks are not this smooth, and I'm going to show you how to adjust for that as well. But I thought, you know, what a good way to do one. I'm just going to randomly orient this, okay? Here's my Brunton. Now, when you go to do this, you want the bubble and the yellow and the bubble and the green to be level as you can get it. Now, obviously, you're not going to be able to see that here. You might be able to. Here. Show you. Okay, so that's going to be about where my... this is more difficult with one hand. Okay, so my strike's right about there. It wasn't perfectly level, I know, but it's really hard to do with one hand. So I'm going to level it now using two hands, and I am going to draw where my strike is. And the reason why I'm going to draw, and I'm going to use a pencil, I'm going to draw is because I'm going to use it to get my dip, even though, whoop, we got, okay, so my strike is right there. And I'm actually facing south, so I'm reading south 26 east, or south, I'm reading south 26 west, but the opposite of that is north 26 east. So my strike is north 26 east. I'm just going to write that down. You should write that down, immediately, just because most of us can't remember anything like that. Here's my pencil line that I drew. It's a lot easier on rougher surfaces to see. It's right here. You probably can't even see it. I'm not going to draw on this thing in marker. Sorry. But now your dip, remember I said it's perpendicular by definition of strike. So you line up that line with this side and that corner of the compass. Then you move your inclinometer until the green bubble, you only got to concern yourself with the green one now. The green one is level, and I have 44 degrees, but which direction? Is it to the northwest, or is it to the southeast? Well, it's a quick way to do that. You can just put it here. In this case, it is to the northwest. So I have 44 northwest. So the orientation of this rock surface, as it sits right now, is north 26 east, dipping 44 northwest. All right. And so that was a nice, ideal one. But what if we have a rougher surface like this amethyst on the iron carbonate of Gunflint Formation? Say this is our surface. Oh boy, what do we do? A lot of people carry a clipboard with them in the field, but really what you could do, there's another way to take strike and dip. This also works really well for low angled rocks. You can't really level out, I mean, this thing can only get you to about a strike as long as your dip is greater than 5 degrees, unless there's a little trick you can do. Well, you can just do it this way. Make sure your clinometer is set to 0. So your clinometer, this part, and that moves it, by the way. So your clinometer is set to 0, and you just put it on the rock until that green bubble is level. Now it's a little hard to draw a line on this kind of rough surface, so what you could do is you could just put a clipboard or a book there, and you can draw your line that way, and then you can measure it directly when you get both bubbles level. And in this case, I have north 10 west. North 10 west is my strike. And my dip, I'm going to make sure it's flat against the rock so I can get my dip. (47 degrees to the southwest. So in this case, my strike and dip is north 10 west, 47 southwest. Quick side note about the Brunton too, because this is also important, I forgot to mention it. This little knob here on the back. You stick a penny in there to turn it. And what that does is that rotates your graduated cylinder so you can adjust for magnetic declination. All right, so you don't even need to worry about that. If you can look up the magnetic declination of your area, and there's a website, the NOAA website has a magnetic declination calculator. You put in your longitude and latitude approximate. Doesn't have to be perfect because the Brunton's only accurate to about half a degree anyway. So, but this one is set for where I am, which is roughly 4¼ degrees, but mine's set to 4½. If you can see it right here, 4½ west, because your declination can be east or west. If you look right there, see that's not at 0. I've moved it. That compensates for magnetic declination. So what that does is that means when I take my strikes, they're always to true north. But I forgot to mention that. Okay, I'm going to do strike and dip one more time on something that's nearly vertical, and I'm getting somewhere with this. But this will also get you a chance to see how this process works on a larger scale here. So I'm going to put my compass down, and I'm not going to level both bubbles. Although it's like right there. It is right at it. Okay, so I guess I am leveling both bubbles. I was going to do the other way, but I don't need to for this. So I'm going to try to do this without marking this up. So that's my strike, which in this case is north 85 west. So my dip is going to be perpendicular to that, which in this case will be to the northeast. So I'm just going to set my inclinometer, which is set at 0. I always reset it to 0 after you get a measurement. And in this case, my dip is 83 northeast. So my map symbol, let's make that a little bigger, would be, oh, I butchered that. So my map symbol would look like, something like that. If I was to write it graphically. But then I still gotta say which way is north, which in this case would be still that way, still north. So that's my graphic representation. This is it written out: north 85 west, 83 northeast. Well, what do I do if my bed, because 83 is really close to 90, that's vertical. You can also have what's called overturned beds, but that's a talk for another time. Okay, so if our orientation was the same, north 85 west, but our dip was vertical instead of inclined, how would we write that? Just 90. You don't need a northeast or southwest in this case because it's vertical. It's just straight towards the center of the earth. So that's where you stop it when you write it. So how would I write that graphically? Just a same thing, strike, dip symbol, but you also put the dip symbol on the other side, so you know it's vertical. That's the universal map symbol for vertical bed. And like I said, that's all you write it out as. Okay, well, that is pretty much it for this episode. I see Blackie, you helped a lot, buddy. But I'm going to do 2 shameless plugs here. If you are in geotechnical or environmental engineering, but you're a geologist, I wrote this book. It's called Midwest Field Geologist Reference Book. I wrote this, actually, I believe last year. The colors, so you can find it in the field. It is on Amazon, all right? It's only 85 pages, it's in black and white, but this is kind of the book I wish I had when I started out. Some of the things in here, you got table of contents, and I'm actually going to read, there's another chapter I want to add to this, and I want to add a scale bar to this, which I didn't do in this version, but that probably won't be for a couple years yet. Anyway, And the other chapter, if you're not putting in water wells, I don't think it's going to matter much. But, I mean, it starts out, you've got general reference, you got weights, measures, conversions, you got geologic time scales, lithographic symbols. I mean, you got magnetic reversal charts. I mean, this is designed for the Midwest, so you've got common graphic symbols for doing strat columns. It goes on for several pages. And unlike that big, thick field book I showed you that from Right in the Rain, I did my own. They're bigger, and I also have not just light against or dark against light background, but I have light against dark background and mixtures of light, dark, and medium tones, so you can get percentages a lot easier. That goes on for several pages. Wentworth compared to USCS, grain sizes in Wentworth with actual graphs, common geologic equipment like I covered today. I also have major structures in the Midwest. This is the area of the Midwest. And I also have major provincial and state surveys where they're located. Contact information on that. There's a lot in this book. Like I said, it's only 85 pages. I also have how to take rock core logs, soil logs. I give comparison of crappy, poorly written logs compared to well-written logs. Different terminologies. I go through some engineering things, like with rock cores, like RQD value, rock quality. If you don't know what they are, then you don't need to, and it's fine. But yeah, just stuff like that. But it actually covers a lot. Classification scheme of rocks, sedimentary, igneous, metamorphic, with actual pictures. And then places for notes and stuff like that. So if you want it, it's not even that expensive. Get it if you want. It helps me out. I like making these things. It helps, my non-for-profit, which is mige-web.org. It's been an official non-for-profit since 2009. So there's that. And I just mentioned my website. And then the website has a lot of the work I've done. It doesn't have all the books. There's actually a lot of books I've written. It doesn't have any of the papers I've written because only one is open source journal, and I'm a co-author on that. I'm not lead author. My other papers where I'm lead author on are not open source, but if you Google my name, they'll come up. But you have to pay for those. And I'm not giving away free copies. Sorry, because they need to keep going too. But yeah, everything on my website is free. Check it out if you can. There's pictures, there's maps, there's an interactive Google map. There's a lot of stuff there, and like I said, that's all free. But I mean, I have to pay to keep that website running. So if you, I'm also going to put a couple links to some of my other books here, so if you want to buy any of them, feel free to. I got 2 more coming out this year too. I wanted to get one for Trans-Canada 17 up to Wawa to 101 to potholes. I wanted to get out before Canada's 150th, but obviously that's passed. It's basically written, it just needs to be edited. The other one's going to be a roadside geology book of Illinois, which I actually wrote years ago for a publisher, but they didn't like my writing style. I guess it was too technical. I don't know. So I'm going to independently publish that, since several people did put a lot of time and effort into making the diagrams for that book. But anyway, that is it. And Blackie and I hope that you learned something.